Hey everybody, today's lab we are going to be talking about the empirical formula of a compound. Now remember that when we're writing the chemical formula for a compound, there are two versions of this that we can write. There are the empirical formula, which shows us the lowest whole number ratio of all atoms that are present in the compound or the molecule. There is also the molecular formula that we could write, and this shows us the actual ratio of atoms in a molecule. Now, remember, for an ionic compound, the empirical formula is the molecular formula because we're talking about a charge balance whenever we write the formula of an ionic compound. So we want that lowest whole number ratio. For all covalent compounds, the empirical and the molecular are related to each other, but they do not have to be the same thing. Today, we're going to talk about an ionic compound that is made from magnesium and elemental oxygen, the oxygen that we breathe in our air. If we were to theorize what this synthesis reaction or this metastasis or this combination reaction is going to produce, we would expect that this metal and this non-metal would produce an ionic compound. Now, we know that magnesium almost always forms a +2 charged ion, and oxygen always forms a -2 charged ion. So we would expect that the empirical formula of this compound would be MgO. Today in lab, however, we want to prove that that's going to be the case, and we're going to do it using math. We're going to do a little experiment and work backwards to determine that this is the case. Okay, to complete today's experiment, we're going to need a lot of equipment to make sure that we can do this safely. First thing we're going to need is a iron ring stand. To go with that, you're definitely going to need an iron ring. You're also going to need a piece of wire gauze, a clay triangle, a functioning Bunsen burner attached to some gas tubing, a crucible with a lid, a small piece of magnesium metal, and a small strip of sandpaper, as well as a pair of crucible tongs, your normal personal protective equipment, which includes a lab coat, gloves, goggles, and you're going to need something to light your Bunsen burner with, whether that's a striker or a... Okay, so to start setting up your reaction today, you're going to need to take your ring stand and attach your iron ring. Go ahead and leave it way up top because we're going to light a fire under this, and we don't want this to get warm until we're ready for it. Okay? Next, we're going to take our Bunsen burner, and remember, for safety, we always completely close our Bunsen burner whenever we first get it. Then we turn it 2 big turns on both the bell and the gas inlet. Then we attach it to the gas main. At that point, we're ready to start trying to light the fire. So remember, we strike our match and hold it just off to the side and turn on the gas with gusto. Don't be afraid of the gas, okay? As long as you're standing back, you're going to be fine. Okay? Then we're going to begin doing adjustments until our flame is a stable 2 blue cones. Okay, now that we've got our 2 stable blue cones, we're going to bring our iron ring stand back in, place our fire onto the iron ring stand, and we're going to lower the ring. We want to lower the ring such that the inner blue cone is just on the inside of the center of the iron ring. Okay? Once we've done that, we can start tempering, which remember, tempering means we've got a big temperature differential here, so we want to make sure that things are warm before we stick them in the very, very hot fire. Okay, so we're going to temper our clay triangle, then set that down, and then now we have an extra step that we need to do. These crucibles are very, very absorbent. They're very porous. So anytime somebody has touched them with their hands, oils and debris and skin cells and things like that can get stuck to the outside or the inside of your crucible. We need to get that cleaned off, and soap and water is not going to help us here because that soap and water can also get stuck in those pores. So we need to figure out a way around that. We've already got fire, so we could just burn it off, and that's exactly what we're going to do. So we're going to take our crucible and we're going to obtain its mass before it's burned. Then we're going to heat the crucible for 10 to 15 minute increments and cool it down and weigh it. And we're going to continue to do that until the difference in the mass of the crucible is very, very, very small. This usually only takes 2, maybe 3 heatings. Today, we're not going to show you all of those because that's 15 minutes on the fire and then 10 minutes to cool, a couple of minutes to weigh, then 15 minutes on the fire, 10 minutes to cool, okay? So instead, I'm just going to show you that we can put our crucible into the heat. Notice I didn't drop it directly onto the hot fire. I'm tempering it, I'm heating it up, I'm warming it, and then I'm going to put it down. Now, notice the bottom of the crucible is directly in that hottest part of the flame. We've got to get this crucible scorching hot. It's got to be hot enough to ignite metal, okay? Once we're on the fire like that, we can put our lid on. We want to set the lid slightly ajar so that we still get some gas flow in there. All of those ashes and soot that burn off can get out, and we can start to get a consistent fire on our crucible. Okay? So we're going to heat and cool this crucible several times until the mass of the crucible doesn't change after 2 successive. Now we have our crucible clean, cooled down. We've obtained the mass of the crucible and the lid. We then obtained a small ribbon of magnesium, and we took our sandpaper. We just lightly went over the exterior of it to take off any residual oxides, any rust, anything like that that's sticking to the outside. We're going to slightly curl our ribbon. We need this ribbon to sit really tightly against the bottom of the crucible. So we're going to curl it up into a smiley face shape, and then we're going to drop it right into the bottom of the crucible. We're going to weigh the crucible with the magnesium and the lid so that we can obtain the mass of the magnesium. Okay? We've done that, and now we're ready to actually start the chemistry portion of this. We need that magnesium to ignite in the presence of oxygen. So we have oxygen all around us, more oxygen than we'll ever use for this experiment. So we have a whole lot, we have an excess reagent of oxygen. We're going to take this magnesium ribbon in the crucible. We're going to gently, again, we're going to temper it. We're going to heat it gently. And then slowly put it back into that hottest part of the flame. Now, when the magnesium ignites, some of the ash from the magnesium is going to try to fly off. We need to catch that, but we still need oxygen exchange. So we can't just set our lid on tight. We need to, again, put our lid on sort of at an angle. That's going to give airflow to the magnesium, but still trap all of that magnesium ash, the magnesium oxide ash that may fly up away from the magnesium. After this, it's a waiting game. It can take anywhere from 5 minutes to 45 minutes for that magnesium to get hot enough to spontaneously combust, because that's what we're waiting for here, spontaneous combustion. Okay? So we're just going to set this here, leave it, wait.
waiting. We're still waiting. What we're waiting for is we're waiting for that flash of magnesium fire. Okay? We'll see a bright light sort of come up out of this thing. We won't see fire, we'll just see a bright light. Once that's happened, we know that the magnesium has ignited. But that doesn't mean that the reaction is over. There's still going to be little bits of magnesium that are going to take longer than others. So what we're going to do is periodically, once we've had that bright flash, periodically we're going to come back in and we're going to look every 2 minutes, and we're going to see if there are any embers glowing, just like in a normal campfire. We're going to look for embers. If there are any red glowy bits, we're not done yet. We're going to let those continue to burn. Those are still going, so we're waiting. And we're back. So it ignited, there was a bright white flash, and then a dull yellow light that calmed down to a red glow. We let that red glow go and go and go until the red glow went out. And when we were done, it looked like this. Now, the problem with this is that that's not all magnesium oxide. About 70% of Earth's atmosphere is actually nitrogen, not oxygen. And part of that magnesium compound is actually magnesium nitride, Mg3N2. That's not what we want. However, there is a solution here. Magnesium nitride in the presence of water will convert to magnesium hydroxide, MgOH2. Magnesium hydroxide can be dehydrated. If I heat it intensely, water will come off of it and we'll be left with magnesium oxide. So that's what we're going to do. We're going to take that magnesium nitride and we're going to add some deionized water to it. Okay? The deionized water is going to convert the magnesium nitride to magnesium hydroxide. Then we're going to put it back on the heat and we're going to convert the magnesium hydroxide to magnesium oxide. So first, I don't want squishity slashity, so I'm going to move the gas out from under that, and I'm going to give this a second to cool down a little bit. Then I'm going to take one dropper full of water. This is way more water than is actually needed to do this conversion, but I want to make sure that I get it all. It's better to have an excess of one reagent that I can have excess easily than to not have enough. So I'm going to put my water in here, and we're going to notice steam coming out immediately. And just drop by drop, I'm going to add this water to our magnesium compound. Now, that's more than enough water. So my magnesium nitride is now quickly converting to magnesium hydroxide. Give that a second, let that conversion happen, and then now we're ready to convert that magnesium hydroxide to magnesium oxide. We do that by adding heat once again. This time we're just going to have to time it. There's no visual indicator that the reaction is over. So we're going to heat this intensely for another 10 minutes. During that 10 minutes, that magnesium nitride to hydroxide to oxide reaction is going to happen. When that's over, we now have our final product and we're ready to obtain its mass.